Okay, I think we can get started. We're happy today to have Otari Sakhelashvili from from the University of Sydney. Actually, Otari's doing a tour of the US. He started in LA, here, and then he's going to the East Coast after this. And today he's going to tell us about some recent work with Gia and Archul Kobakidze on Theta-vacua quantum gravity and the particle spectrum.
Thanks for the invitation, first of all. And I will talk about a lot of different stuff. I will try to squeeze my talk. Mainly, these are the two papers on which I will talk. And let's start from the beginning. So, everyone knows GR and adores it. So, classically, it is given by Einstein-Hilbert action, which is quite simple because if we take variation with respect to metric, we get dynamical equations of motions. And we can solve those dynamical equations of motions and we get different space times. Then in GR, we have superselection. We have three different options, what kind of space times we can have. One is de Sitter with positive cosmological constant. Second is anti-de Sitter, and there is Minkowski. And in classical GR, those are considered as an empty spaces, so spaces without anything. And if we want to consider some matter or itself or gravitational fluctuations, we should consider on top of that. Those fluctuations in fundamental theory should be understood as some expectation value in maximally classical state of the quantum operator. So in the example of Minkowski, we just have Minkowski vacuum. On top of that, we have graviton, and gravitational wave should be understood as expectation value of the operator between some coherent states, which correspond to gravitational wave. So that is the picture, naive picture in GR, extremely simple and extremely boring. Now, if we start at considering non-perturbative quantum effects, we realize that de Sitter has a temperature. So we realize that de Sitter evolves in time. Even if we take the static patch, de Sitter will evolve in time, and that will be incompatible with quantum description, because in quantum description, ground state should not evolve in time. Ground state should be eigenstate of the Hamiltonian. So in that sense, eternal de Sitter is not compatible with quantum gravity, and eternal de Sitter should not be considered in this superselection settings. Meantime, non-eternal de Sitter is completely fine, and non-eternal de Sitter can be understood as a state, excited state, built up on top of Minkowski. And how we distinguish eternal and non-eternal de Sitter? Well, quite easy. There is so-called notion of quantum break time. Whenever we reach this time, then we should distinguish between eternal and non-eternal de Sitter. And if the theory is consistent, after that time, de Sitter should deplete, like in the case of the inflationary universe. After a certain time, we have graceful exit, and that graceful exit should be below this time. But from here, we see that we can still manage to take this time to infinity. So we can still make de Sitter eternal, right? For that, we should fix the Abel radius, because that is parameter of de Sitter, which is same as de Sitter radius, inverse of that. And we should bring and plug to infinity. Then we have rigid eternal de Sitter, which doesn't contradict anything, but meantime, all the quantum gravity is decoupled. Because quantum gravity interactions, gravitons, as you know, interact derivatively. Their interacting strength, like in the case of ions, is exchange momentum over M Planck. So if we bring M Planck to infinity with any finite interaction rate, gravitons decouple. So this is not plausible exclusion, And if we see something like cosmological constant, we should immediately think about an inflation. So this sets, let's say that the theta is not part of the quantum gravity, at least eternal. Non-eternal is okay. Now, in ADS cosmology, we have big crunch, which is cosmology with future singularity.
Are you saying that from this perspective, pure GR with a positive cosmological constant is like in the swampland that cannot be repeated in the
Yeah, unless cosmological constant is resolved with something. For instance, we think inflation. Yeah, that's exactly what I'm saying.
Well, it could be a dynamical field too.
Yeah,
It could be
absolutely.
a roll.
Absolutely. Unless it is like this, and it is a rigid cosmological constant, it cannot be. Yeah. And yeah, lot of people, there are lot of references. Yeah. But the argument is the following: this there is not a ground state because it has temperature. So ADS doesn't have the similar problems. ADS can be ground state, but it doesn't support cosmology because it has singular feature. So in ADS we cannot do cosmology, and ADS, if we want to keep our cosmology, ADS is not a plausible choice as well. But of course, ADS is supported by ADS CFT. So empty ADS or supersymmetric ADS, isolated ADS is completely fine. Also, I want to single out that if we want to formulate gravity via S matrix, the formulation which we have or string theory supports it, then we have singled out the Minkowski vacuum. So quantum gravity will tell us that we should be living in the Minkowski vacuum. And let's take all this input and let's try to take quantum gravity and add other ingredients. Now, let's imagine that we tune cosmological constant. It's fine, now we are in Minkowski. Our job is done, right? Naively, we would say that, okay, we tune cosmological constant 0. Our job is done. We are in the Minkowski vacuum, and we have quantum gravity, which supports cosmology. So we are in the framework where everything is okay. But is it? Well, it is not if we have choice of different multiple vacuum. Then what I mean, if we have solutions in the theory of different vacuum, who are familiar with QCD, there we have such solutions. In QCD, we have Theta-vacua. I'll discuss who is not familiar with that, what they are. And for different thetas, we have different vacuum. It means even if we tune cosmological constant for one of them, neighboring ones will make the theta, which is not acceptable because we wrote down theory, we wrote down Lagrangian of GR plus QCD, and now whenever we solve and all the different values of thetas are solutions of the theories, we appear in a paradigm where we bump on non-consistency. No, I tune once at all, then different thetas are solutions of that theorem.
Well, you can tune it all together.
No, I can.
To be in one vacuum, you can tune it.
For one vacuum, yes, but other ones are solutions as well. Let's imagine, for instance, quantum electrodynamics.
But then there is super selection.
But can you show why theta not equals to 0? It is the theta.
By Vafa-Witten theorem, if I tune theta equals to 0 to be Minkowski, then each of the theta brings vacuum energy.
Okay, it means vacuum energy, but why it should be the theta?
It's vacuum energy, it's rigid vacuum energy, so it has
No. What means
for me, it has as a cosmological constant. if I tune everything to 0, and now I have vacuum energy, which is uplifted from that, that is the
Not the vacuum is zero. No?
theta 0 is the vacuum, which is 0,
The
but
vacuum is the
if
same.
No.
different from theta.
No, but it's different from 0. It's not breaking of anything if you do not have supersymmetry. So it's not about breaking. So you are talking about what? Preserving supersymmetry or preserving Minkowski?
No, I tuned everything down to Minkowski. I don't
Right,
have
but
supersymmetry there.
but vacuum energy could be non-zero in Minkowski. Why not?
Because vacuum energy then will couple with the metric and it will produce the theta, right?
But it's what I'm trying to follow. You mean that it's automatically would be the theta then? So with vacuum energy non-zero?
Yeah,
Because
because it will be positive. That
no, but
vacuum-
it depends how you couple gravity. Maybe gravity is not coupled to this energy.
But if I will write down the minimal model, which is gravity plus QCD, it will automatically couple. There is no choice now.
I see. So you're, but okay. So in this way,
If I have GR plus QCD and I
Uh-huh.
choose cosmological constant to 0, every solution of the theta-vacua, whenever theta is not 0, will sit in the theta.
Yeah, but it could be non-physical because some to give you an example that say okay let's say that we have this longitudinal photon which is not physical. I mean that not coupled to anything in electrodynamics, right?
Right.
But then you can say, aha, those photons are still coupled to gravity, right?
Not really, because gravity will couple via energy momentum tensor, right?
Yeah, right. And this longitudinal photon do contribute to energy momentum tensor, but they are not observable.
Right. If you are talking about the massless photon, absolutely, because gauge redundancy or BRST invariance removes completely that.
No. Let's okay. Let's make it different way. Start from massive photon, normal massive photon.
Yeah,
Okay.
then I can create photon with polarization 0 or spin 0, better to say.
Right.
And they will, for instance, scatter via gravitational interaction, which
okay. So okay. So what I'm trying to say is that then those in the limit of mass goes to 0, the only interaction you will see is an interaction with gravity, right? Because
absolutely. Absolutely. I will see a Goldstone which interacts with gravity. Yes.
Yeah, right. But okay, and it could be the case, but we are at the moment we do not have a way to measure this, right?
Sorry?
No, I mean we do not see experimentally.
We don't see it, but I'm talking about the conceptual things, not observational things yet.
I see. So then you are saying that in this way we will see this the theta as appearance of this longitudinal photons, for example, right?
No, longitudinal photons will not create the theta because they are degrees of freedom.
Yeah.
Unlike the theta vacuum, whenever theta vacuum is freeform, which doesn't carry degree of freedom, and it creates constant vacuum energy.
No, right, but longitudinal photons, if you have a density of them, would also create.
Density, yes, but I'm talking about the vacuum.
Okay, okay.
I'm talking about the vacuum, about the ground state.
Okay, I see, but in this sense, in our if without gravity, this state which has density of this longitudinal graviton would be not different from our ground state. It would be the same, right? We cannot differentiate them. But
no,
then you are saying
we can still do. We can do scattering experiment on top of them, and we can
observe. Or experiment with scattering of graviton.
Via graviton, right. And gravity is in the game.
Yeah. Okay. But okay.
Yeah. And questions? Yeah. Okay. So even if we tune this one, then other ones will be in the theta. So that's the problem, because I want that QCD works for its all solutions, and each of theta vacuum is a good solution of QCD. Then we know how to lift the super selection. It's called how to solve CP puzzle. And in this scenario, CP puzzle is not puzzle anymore, but it's consistency. If strong CP is not solved, then QCD and gravity don't work together. That was the claim which was made actually recently. Now, let me remind you what is this QCD, what are the QCD vacuas, very briefly. So QCD is based on the gauge group S2N color, and those gauge groups have non-trivial homology. So naively, we would say that we have distinct different vacuums. Like, for instance, in double well potential, we have distinct different vacuums, but non-perturbative effects, namely, for instance, instantons, tunnel between them. So none of them, actually, the vacuums classified by this homotopy group, none of them are the real vacuums. The real vacuum is superposition of them, Fourier transform of them, and it is given by the theta parameter. So we can build a continuous amount of the different vacuums. That continuous amount different vacuums appear at the level of Lagrangian via this term. As you see, it violates parity and CP. Yeah?
Confusion here. Theta is not a dynamical field in this context. So
No, it's not.
Unlike a situation where you have like a double wall potential, where
Right.
you can talk about the value of the field and where is it the minimum and so on. Here it's like an argument by analogy. Theta is a fixed parameter once and for all.
Absolutely.
Right. So
Absolutely.
I guess I didn't understand the previous slide because like
In previous slide is the following.
yeah. That's the parameter, right?
If I have Lagrangian, which is GR plus QC, then that Lagrangian has infinite amount of solutions. Name me one theta, that would be solution of that Lagrangian.
Most of them violate CP. So if we just have gravity plus
that will violate it.
There's zero.
Except these two, all of them violate CP. Pi, it's little subtle because, okay, then we don't know how to define QCD value. Okay. All the different thetas will violate CP. But all of them are solutions, and all of them should serve as a ground state of QCD. Would you agree with that?
No,
If I have pure QCD.
So no, but perhaps my disagreement is linguistic. So why don't you go on? Go on. It's okay.
No, let's agree on this because this is important. If I have QCD, if I have just QCD.
Yes. It doesn't make sense. Well, the thing I'm objecting to is that so to say I have a solution, I get to pick my dynamical fields. But to say I have a solution, solutions can be a function. I get to pick theta once and for all. It's not a dynamical.
Right. But it's a choice. It's a
Yeah,
we
but
can
most of
choose.
those choices
In the
are
case
consistent.
of the double well potential, we have just one solution. The ground state is unique.
But
So we build antisymmetric and symmetric. One of them is lower and it's unique. In the case of QCD, because of super selection, the ground state can be different. We can choose any theta and any
what I'm
theta.
saying is, if you assume, I don't know if you want to assume CP is a good symmetry.
No, I'm not assuming.
Okay.
I'm not assuming. I'm just stating that if I have pure group, even not even QCD, if I have pure group, for each choice of theta, this is legitimate ground state for which that theory works.
Yes, I agree.
And those are solutions because I just need to specify QCD Lagrangian, then I will find those ground states as solutions. Once I choose one of them, there is super selection. Similar to quantum electrodynamics. Quantum electrodynamics, once I fix the charge like coupling, then I have different solutions. 1 electron, 2 electrons, 7 electrons. There is super selection. From 7 electrons, I will never get 2 electrons. But quantum electrodynamics works for each super selected set. I can scatter 7 electrons, I can scatter 2 electrons, it works well. but this is different superselection. With dynamics, I will never go from one to the other. In QCD, it's even more. I have the theta parameter or theta number. For each theta, I have superselection. From one theta, I will never go in another. But theory should work for each of them. That's the same.
Okay, I still don't understand procedurally why I can't take any theta. There
Right.
will be a contribution to the vacuum energy, and I will treat my initial lambda
Right.
as a sort of a bare parameter that
Yeah.
I will adjust to the
Right.
so that the entire thing is zero.
Yeah, for
Sure,
any given theta.
For any
But
given
each,
theta.
the theory should work for each of them, for each solution.
Why
We
should it
cannot
work
say
for-
I like
why
this
should it work
solution.
for each of them? Why should like you pick theta once and for all? Having picked it, live with it. This is
Sure, sure, but the
So-
theory is specified without theta. Theta is a solution. It's similar to say in quantum electrodynamics, I like charge 5, but I don't like charge
What's
11.
the difference if I have, say, where, you know, my potential is such that it goes negative at a certain.
Because it's not a solution, it's a parameter in the
Then
theory.
we know that we can always choose a lambda such
Sure.
that together they're
Sure.
zero,
But
right?
yeah, I mean, lambda is a counter term. Its value, it's a bare parameter whose value depends on your choice of other coupling constants and whatever.
Right.
And you
Coupling
want-
constants not solution.
Yeah, you want to fix the physical value of.
Sure, but I cannot say it works for one solution and it doesn't work for another.
It's not
That's what I don't understand.
independently observable, right? It's
No.
observable only in combination lambda plus some constant times theta squared.
Yeah,
Sure.
exactly.
Sure, absolutely.
So
But
I
the
can-
thing is, I should be able to choose any theta which I like.
Yes, but you cannot choose anything.
But
you
I
like and
cannot
do
choose
lambda.
any lambda which I like.
Why not?
I should just
Why
fix
not?
it and that's it.
No, why
Because
not?
lambda is a parameter in the theory, theta is a solution. There is big
Uh,
difference.
May I ask you, I believe that that atom by itself, it's kind of topological invariant. So if
Yes.
I look at that atom itself and change in metric, it does not change that atom, right?
Right.
It means that if it will be that atom by itself, the gravity is not coupled to this atom directly. It's only
No,
coupled
but
to.
it's coupled because there is topological susceptibility which generates the energy.
No. You can say it in different way. You are saying that because of theta, you have vacuum energy, and vacuum energy is coupled to gravity, right?
Right, right.
Right,
It
but
doesn't couple with topological term, of course, because then it would couple with electrodynamics on the similar term. But
Yeah.
it couples on, or let me make another example. If I have a Schwinger model, then different electric fields are different solutions, and electric field is from 0 to 2 pi, right?
no, but electric field is the same at theta there.
Right, exactly. So, and Schwinger model should work for each electric field.
Right.
Yeah, so it means if I have properly defined Schwinger model plus something, for each electric field, it should be well defined. That's the statement. Okay.
Yeah, no, but in some way it's a different part of sector. So because different electric field is like a different universe in Schwinger model because they are not
Absolutely.
coupled.
Like here, the different theta is different universe. But
You're right.
but the
Agree.
theory should work for each universe.
Yeah, separate. Right. That's true. But they are not coupled to each other.
Absolutely not. Yeah, because there is super selection. Like
Yeah.
electric charge 7 is never coupled with electric charge 2.
Mhm.
Right. Okay. Now, so the theta 0 is a minimum energy by Waffa and Witt. And there is so-called strong symmetry problem, which can be solved via chiral symmetry. So if we have chiral symmetry, by chiral rotation, we can redefine the theta, which means in that case, theta is not physical. Or in other words, we have charge non-conservation due to instantons or due to index theorem, and the chirality flip is absorbed in the instantons. So if we have chiral symmetry, theta is not physical, and we sit in a unique vacuum, which is theta equals to 0. Then, in the case of the chiral symmetry, we don't have necessarily massless quark. We can have massive quark, which was realized by Pacheco-Quinn symmetry, if we have some field which has the phase. And that phase absorbs the chiral rotation, and this field is called an axion. Now, that is tip of iceberg how this really works. And let's look it up how that really works. This object is called topological susceptibility, which is second derivative with respect to theta, and it is just correlator between these two quantities. As you know, this quantity is a total derivative since it's topological. So by Kellen-Lemma representation, here should be t squared. And by Kellen-Lemma representation, here we can put only propagators. So if the strong CP problem is not solved, then this quantity, topological susceptibility, is not 0. And here we have the massless pole found by Lucian. If this quantity is 0, the only way to make it 0 is to shift the pole by some mass. If strong CP is not solved, then this pickups vacuum expectation value, which is proportional to theta, similar to the Schwinger model. And axion or the chiral symmetry in general, massless quark, makes theta unphysical, fixing this correlate. This can be understood as three-form Higgs effect. And the U1 problem in QCD is solved exactly like this. If we combine a Goldstone with this correlator, we get a massive scalar. And that's exactly what happens in QCD. We have a Goldstone eta prime, which is coupled with this correlator. This correlator gets mass due to that coupling, and eta prime is a massive scalar. So, then in our context, where we want to make theta unphysical due to gravitational demand, the chiral symmetry should be exact. We cannot leave this correlator to be non-zero because we create a de Sitter. So in that sense, solving strong CP problem is a consistency problem, and the axion quality problem should be exact. So there is no escape there. And Gia has this type of solution that instead of the usual conventional axion, he was using two form again propagates one massless degree of freedom, but it's really hard to spoil it via high dimensional operators. So maybe that will be a good axion in order to solve this problem. Now, that was an example for the purposes where I'm going. Long ago in gravity was found instantons. They are called Eguchi-Hanson instantons, and I will try to convince you that those instantons will work in the same fashion like the usual instantons work in QC. So, this is a Euclidean metric of gravity. At infinity, whenever r goes to infinity, that metric is like the Euclidean metric, flat metric. And as you can see, we have this type of vacuum solution for Euclidean GR, and it has some bound. So A, we can imagine as a size. And this is solution of pure GR in Euclidean space. Only interpretation, what this guy can have is an instant. Now, let's look at this topological problem. First of all, it has zero action, but pardon for that for a moment. I will fix it up because instantons will not make sense. Any semi-classicality doesn't make sense if it has zero action. I'll patch that. Now, at infinity, it has boundary S3 over Z2. Immediately, pi3 enters in the game, like in the case of the QCD instantons. And since it has coordinate singularity, which should be removed, it's a two-sphere. So it can be characterized by two topological invariants. One is Euler characteristics, and since near the singularity, it behaves like two sphere is two. And second is Pointryagin index, like in the case of the instantons. But instead of GG dual, now we have RMP. So this type of instantons will generate non-trivial vacuum for the GR. Even if we set cosmological constant 0, we will have non-trivial vacuum. Now, instantons, as I said, should have finite action. So as soon as in the action we have total derivative, topological term, chi, which is not 0 for this instanton, then the solution is the same, because in variation this doesn't take any contribution, and transition amplitudes will be given by this number. If we canonically normalize the graviton, then this number can be understood as a cutoff of gravity in the units of M4, which means setting this to 0 is not good idea, because it means we are bringing cutoff of the gravity over the M1, doesn't make sense. And this should be large number, because cutoff of EFT should be below of M1. So these instantons in
Да.
Засыпаю. Ты слушаешь?
Да,
Извини.
да.
Ну, ты меня слышишь?
Нет,
We
не
have
надо.
the Einstein-Hilbert term, which is a two-derivative term.
right,
Then we have these
Chi term.
chi term, which is formally four derivatives, right?
right.
So now
But this is topological.
yeah, it's topological, but bear with me for a second. So the Einstein-Hilbert term has a m Planck squared in front of it, and then it's an expansion and inverse powers of m Planck. So the four derivative term should have no m Plancks basically. So
Yes.
C is some dimensionless thing, consistent with what you're saying. But from effective field theory, I would have guessed that C would be order 1, and here you're saying C is large.
C is actually parameter,
Yeah.
but I'm saying it should be large. And if we normalize graviton canonically with 4 and Plancks, then dimensionality of C will be this.
Yeah, but what's this parameter lambda G? This is a
That we are
parameter.
calling gravitational cutoff, in which we can reparameterize C.
Yeah, that's m Planck. That's what I'm. That's what I'm
That's his
saying.
question. And Planck,
Yeah,
the gravitational
I was
cutoff.
too-
No, I can bring gravitational cutoff to low if I will include a lot of species of particles. So gravitational cutoff can be always lower than in Planck.
He's adding a lot of degrees.
But what is lambda gravity? It is levitation cutoff?
Right, but I'm leaving this as free parameter for a moment.
No.
These are free.
But yeah, so is it so
Okay, this bar barely works. Whenever it's big, okay, this instanton is well trusted.
no, but just a moment. What means gravitational parameter? C is dimensionless number, right? So
Right.
your parameter is just a dimensionless number. It's not not cutoff, no whatever. It's just number.
Right. But I
I
can't
see.
write this number in the units of Planck.
No,
If
of
I
course.
canonically normalize the ground.
No, but then lambda gravity which you introduce has some meaning or whatever. I'm just trying to follow what you.
Lambda
what you-
gravity is cutoff of my EFT. So if you wanna have some lower cutoff of my EFT, then I should take C to be large number.
Okay,
If
say
I take my
QC.
cutoff to be M Planck, then C is 1.
Okay, let's say you have QCD. You have lambda QCD. It could be lambda gravity.
No, I'm talking now about pure GR. This is in pure GR.
I see. So no,
But
no,
lambda
okay.
QCD can be lambda gravity, not in our world, but it can be.
I see.
We have lot of species where we are lowering cutoff scale to lambda QCD, sure.
So this is like an extra dimension.
Okay. So
Not
but-
necessarily, but yes, like an extra dimension.
No, but I thought that in pure gravity, you do not have so in pure gravity you have mass of Planck as a parameter, and now you have another parameter which you can see, right? It's another parameter.
Which I can see only via absolutely. This is C new parameter, which I can only see via instantons because it doesn't have
Yeah, I
contribution in
understand.
perturbative physics.
I see. Okay.
Okay. Now, let's talk about the second term. With the second topological invariant, I can add theta gravity term. And immediately I can check that topological susceptibility in GR via this instanton is not zero. And if the C number is big, then my computation is trustable. If C is 1, if gravitational cutoff is high, it's not trustable like in QCD, but still I know that I have this correlate. So there is vacuum angle in the gravitational sector as well.
Yes. Did you just implicitly assume there are no massless fermions anywhere?
I just assume that I only have GR. I will start adding it bit by bit. I only assume GR. GR has these solutions, which means in GR we have this
I mean, on the previous slide, to make it make sense, you need to assume not just GR, but an infinite number of other particles, which were unspecified.
Right.
So if any of them is a massless fermion, then the reason that I'm asking.
On
is
the
saying-
next slide, I will tell you that even that doesn't help, but yes.
Okay.
But on previous slide, I kept myself as generic as I could. Maybe it was mistake. I should have taken C to 1, but I just for generalities I put like this. Now this is physical, and it was suggested that massless neutrinos could get mass, for instance, from there. And again, if we go on the same philosophy that we don't want to have a de Sitter and so on, then this defines new CP problem, which we call gravity CP problem. And we need to solve it. And like you say, it's not big deal, right? I can bring a massless fermion and immediately it will rotate away this angle. And there is so-called Salama normal, which immediately kills this problem and why I even brought this problem, but not so fast.
Sorry, that what you call gravity CP problem is that you would
That I have theta angle.
excessive contribution to.
I have theta angle with RR dual,
Yes,
which makes contribution to the vacuum energy,
right.
and that should be cancelled if you trust my introduction.
All right. So it's not from the fact that it breaks CP, but from
No,
yeah, from contribution to from the square of that.
Right, but it still breaks CP as well. Of course, it
So
breaks
what?
CP.
That's
Right.
That's
That's not a problem, but the problem is square of it. Yes.
Now.
Yeah. Like in the case of QCD, I define strong CP problem with square, not
Well,
because
the
it's not
CP
observed or
problem is because we confront it with observations that
Sure, but
CP
then
symmetry and here
right, but
no
then
such-
peak like up quark really small and theta can be a bit. Still in this framework where I don't want to have an eternal de Sitter, that will be a problem. Okay, so gravity problem is defined in that sense. Now, it would be easy to solve if we have chiral fermion, right? Like in the case of QCD, but not so, because it was found that helicity half fermions don't have zero modes on that spacetime. And it's understandable because they couple to Ricci, and Ricci is zero of that solutions. But fermion with helicity 3½ has exactly 2 zero modes. Which means if I want to make gravitational theta unphysical, in the spectrum I should have fermion 3½, which will rotate away that phase. So it means if I take gravitational CP problem seriously, immediately in the spectrum I should bring fermion with 3½ helicity.
But you have to break the city.
Yes, it automatically breaks actually. Yes.
The index theorem. So there is a term. The proportion to R on the right hand side of the index theorem.
Right, but this has corrections with so-called boundary. Yeah, it has boundary on in the GR you have so-called boundary terms which cannot be written as the bulk terms. It's generalized at a single term.
You mean
But without C-half Feynman, this theta term, gravity theta term, does introduce non-zero vacuum energy?
So,
No, because in your previous example where it was QCD,
Yeah.
remember theta term. Here I can ask the same question, right? But
yeah, it has non-zero vacuum energy. I skipped that discussion, but indeed it has. And theta square, indeed, it is indeed proportional for theta square, like in the previous case. Yes.
Okay, and then you can argue the same way that it would be kind of the theta or whatever, it would produce a lambda term then effectively, or what?
Right, exactly. And
I
I
see.
want to remove that one, and
Mhm.
I'm seeking for solutions. Then helicity, 1/2 fermions don't have zero modes, they don't work. And I'm forced to integrate it
Yeah,
3/2.
this I can understand. Yeah, okay.
okay, so let me just confirm. So you mean the boundary term just cancels?
Yeah, absolutely. It exactly cancels it. And it was mathematically proven by this Eguchi-Hanson. Right. And you can understand differently because the zero mode should be normalizable. Ricci is zero, so it means in the Dirac operator, whenever you square it, there is nothing. But in the case of this, there is Riemann, so there is normalizable zero mode. Now, as soon as we have this guy, it requires gauge redundancy. And gauge redundancy is done via the fermion charge, which means, okay, this fermion charge brings supersymmetry. So consistency of integrating in this guy requires local supersymmetry, which is super. Which means, okay, even without knowing this, we know if we integrate in this guy with gravity, we are in super. So, and here I have a conclusion that if we take gravitational CP problem seriously, we end up with to have super. So if we want to solve gravitational CP problem, we need to have super.
Can you remind me, what is the gravitational CP problem? What makes it a problem?
As soon as this correlator is physical, this guy will generate the theta. Like in the case, like I defined.
No, but you mean the problem is not CP violation, the problem is vacuum energy? What is the problem?
No, this violates CP as well, because like.
Right, but you do not have conditions that CP should not be violated. By itself is not a.
Sure,
I mean, it could be
still have
violated.
vacuum energy, which I want to remove. Yeah,
I see.
That's how I define gravity. Yeah. I see here I'm not convinced.
The things I'm worried about have to do with the earlier example, so don't worry about it. We'll feed her all the.
Right. Now, then this instanton for gravitino will generate hot vertex. There are 2 zero modes, so 2 of them will enter. And it will generate in the fashion of supersymmetry. Which means, okay, our symmetry is broken. We broke our symmetry because we removed theta dependence. Okay. But simultaneously, we are lowered in ADS, which I don't want to happen because I want to live in Minkowski. So then somehow we should uplift our theory to the Minkowski. We are writing paper how this happens in different scenarios, but the easiest one is to bring Poloni model. But from conventional Poloni model, there is a difference. We just need this time. Because W3/2 is generated by instantons. So we just need to write down this potential, which is linear in some chiral. And we end up in the Poloni model, which immediately breaks supergravity, solves the gravity CP problem, and this guy develops vacuum expectation value. And the phase of this guy is axion-like particle, which solves actually gravity CP problem. And the mass of this, if we compute, irrespective of the model building, is degenerated with mass of gravity.
So this constant term is potential, you're tuning it to be.
No, this is generated by instantons.
Yeah, but it's a constant term.
It's a constant, yes.
So you're using that to cancel the CC, because that's what it's normally used.
Right. I'm using this together with those guys. I'm choosing with respect to lambda x that I stay in Minkowski. So in that sense, okay. And it's motivation of this type of dark matter. And also note in our paper, we have this detailed discussion that since fermion halves don't distribute in zero modes, their anomaly should completely cancel, and they should not count with our symbol. They should count with our symbol. So, and we have examples of that, why this should happen, but I don't have now time to discuss this because I want to switch on the other topic. Now, I discussed gravity CP and strong CP. What about electroweak theory? In strong CP, we have eta, if quark is not massless axion as well, mixture of them. In the case of gravity, I argued that we have this gravity axion. What happens with the electroweak theory?
Can you go back to play first slide? I want to make sure what is axion. Axion is measuring part of the skeleton component, right?
The AR, what we are calling, is a phase of this field.
So that's the measuring part of the skeleton component of the Polonium field.
Yes, not imaginary part, but the phase.
Oh yeah, okay. So,
Yeah. Yes.
So obtain gravitational mass.
But not the axion of QCD, but axion of the RR dual guy.
What gravitational mass are you considering here?
Gravitino mass is connected with this C parameter.
So what is GeV or T? What is your gravitational?
That we don't know. On that we are working because it is generated here, and this is given like exponential minus C. I don't know what this C is. That's why I try to make connection of C with the cutoff of the theorem. So if the cutoff is en Planck, then this mass will be en Planck. That's it. But of course, this cutoff should be lower, sure.
So can't you just read gravitational mass from requiring fine-tuned cancellation between Suzy breaking contribution to the vacuum?
No, because this guy is given by exponential minus C. If you give me the number, what is C, okay, then I can tell you what is mass of the gravity. Of the C parameter which I imposed in previous slides, right? Here, this guy. So gravitino mass depends on this guy. Like eta prime mass depends on the exponential suppression. So I don't know. This is free parameter in the theory. We are working to fix in realistic models. If we put the matter sector and so on, we should have to fix it.
So why do you say it's important?
It's motivated.
There's a single constraint on gravity.
Sure, but since it's free, okay, maybe it's good motivated. It's a candidate. I'm not saying it's a dark matter. I'm just saying it's a motivated candidate.
Oh, okay.
Because if we follow that gravity CP problem should be solved, we have in the spectrum those particles, so it's motivated. Not like it is dark matter. Then I would have some plots and production mechanism or something. I'm just stating that it is motivated candidate. Yeah. Okay. Now, what about the electroweak theory? Let's strip it down and have without hypercharge only SU2 sector, which is completely Higgs. And the SU2 sector has weak angle. SU2 sector has vacuum angle as well.
But this is never physical, right? We can just rotate it away.
In the standard model, which you will see on the next slide, yes.
Yeah.
Yeah. I don't have fermions yet, but without fermions, this is physical, right?
I can rotate, oh, without the.
Without fermions. My theory is this. Without fermions, this is physical. Then this correlator is physical.
No, but look, in Anselm Johansson, they are proving that Theta-W in electroweak theory is not observable, right?
Yeah. But
but
if
now,
I'm
now,
integrating fermions.
Yeah, right. Now you are adding gravity. Now the same term, which was not observable, becomes observable.
No, not observable stays unobservable, but I wanna build bit by bit. I just wanna start with the full bosonic theory, then add fermions.
No, before fermion. Okay, you have this term, which was in electroweak theory was not observable. Now let me.
That this is not
Wait. Now you added gravity, and then you would argue again that vacuum energy is non-zero, and this term becomes observable.
Then I will argue that this term will be observable without L symmetry.
Okay, so
I will add B plus L symmetry.
No. Before killing that, you are saying that what was made unobservable.
I don't have gravity as well. Like I will bring gravity. Like
here, right, but it's what I'm asking. That bringing gravity itself, it immediately makes this term observable. Through vacuum energy.
Immediately, if there is no chiral symmetry, yes.
Yeah, right. Okay.
Yeah.
Okay, thank you.
At this moment, I don't have any chiral symmetry.
Okay.
Which means, okay, this correlator is non-zero, and it has Hooge suppression, exponential suppression, but it's still non-zero. In gravitational framework, okay, we should make this unobservable, which means, like in the previous case, like in the case of QCD, we should have some scalar because we need to make this correlator gapped. Which means this correlator somehow should eat up some kind of Goldstone-like particle and become and get gap, like in the previous slides. Now, what if we add leptons and quarks? Then there are two symmetries, B minus L, which is not anomalous. I'm not concerned about that, and B plus L. And B plus L makes this theta unphysical. So we can, by rotating B plus L, we can rotate it away. Meantime, it means this correlator is zero. So that correlator became gapped. Like in the previous case, it has structure P squared divided on P squared minus M squared. So somehow it gets mass, which means there is some kind of particle inside the standard model. As soon as we made it unobservable, there is some particle in the standard model. For a moment, I will call it eta-weak because it's kind of contrapart of eta prime. And let's see what is the origin of this particle.
Sorry, just a question.
Right.
So if I go to a high temperature regime and populate the entire STEM model states, I have a well-specified counting number of states.
Right.
This would be a composite state at low energy, or this would be
composite.
New.
No. It will be composite and
the statement is that
it's a composite. I will show on the next slide how it composes.
No, but still, it looks like this additional particle you're talking about, say, in Anselm Johansson standard model, they have fermions, right? But,
they have fermions which rotate this.
Right. But those fermions still remain in symmetry. There was enough to kill W still.
Right.
Now,
I'm talking about that. Yeah, I'm talking about that.
Right, but now when you add in gravity, you are saying that what they kill.
Gravity. Now I'm talking without gravity. I'm not
without gravity. But
I'm talking without gravity. Without gravity, this guy is zero. This correlator is zero. It means it's gapped, like in the case of QCD. Eta prime gaps the correlator of GG dual. What I'm saying here, it's similar to QCD. This correlator is gapped. So there should be some degree of freedom. And let's look it up for that degree of freedom. That's what I'm saying.
No, no, but then okay. Then you are saying that it is killed due to the existence of this eta W, or
Right.
because
In pure standard model without gravity, it is killed due to existence of the some scalar state. And let's look up where we do have.
yeah, okay, but Eguchi-Hanson, they did not have any extra particle, right?
No, they didn't have any extra
Yeah.
particle. They just say, okay, theta weak is unphysical.
Yeah.
Then
Right.
my statement is, if theta weak is unphysical, this correlator is 0, which means this correlator is gapped.
Mhm.
If this correlator is gapped, we have a composite particle in the standard model, and let's look where it, why we do have it. Okay.
Oh, okay. It looks like you are going very far. Maybe you are losing us on the way.
Oh.
No, I mean that I think that it is kind of sounds as very kind of strong statement, and I'm not can immediately argue against it. But the feeling is that it is it sounds too much strong. But okay, it's my personal feeling.
Let me show you next slide, and maybe we will agree on that.
Just to
Right.
restate it, I mean, normally we can rotate away the
Yes.
angle, so it's
Right.
unphysical, right?
It's unphysical.
But now you're saying that if you have this argument where you couple with this eternal de Sitter, right?
No, without that argument, if I will talk about the correlators, like in QCD, rotating away means gapping this correlator.
Yeah. You want to solve the gravity CP problem by introducing this.
No. I was done with gravity CP problem here.
Even if you stand on Planck to infinity because
Yeah.
of gravity, just a standard model.
But you don't need an eta W for that.
Well, this apparently.
That's not-
statement.
that's
No,
not correct.
like in QCD, I need data prime.
No. You can rotate away.
Exactly,
You
and
don't
what
need
I'm
eta W.
claiming,
You
what
don't
I'm
need-
claiming.
You don't need it. That's what Akadi is also
Right.
saying. You don't need eta W.
Yeah, but my claim is following. If I'm able to rotate, then that symmetry spontaneously blocks.
Yeah, but that's because you're using this gravity argument.
No, I'm not using gravity. I'm using Kellen-Lemon representation of this.
Let's get to the crunch. Let's show us your
Right.
prediction for this.
Now, for simplicity of computations, let me consider one generation of fermions and oversimplify QCD, so remove the code. Then I have one quark and one lepton, which carry B plus L number 1. So if this carries B plus L charge 1 inside the standard model, unit B plus L charge, if there is eta doubler particle, then this guy should generate vacuum expectation value. Simultaneously, this operator is so-called Theta-vacua.
Sorry, is it gauge invariant?
Sorry?
It has one quark. In which sense is this gauge invariant?
You put one color.
Because I put one color. In
One
standard,
color.
if colors is 3, like here will be,
By one color.
because to simplify my
I mean, gauge
computation.
group is E1 for QCD.
No, that to simplify my computation, because in QCD that will be QQQL, which will be hydrogen atom. This operator will be left polarized hydrogen atom. For simple computations, for simplicity, imagine that this is proton and this is electron. Okay. For simplicity, I just put one color. Then this is top vertex. In one flavor standard model, this will be QQQL, and this should develop, if what I'm telling is right, this should develop vacuum expectation value, and it will be full agreement with the index. Now, what happens? Well, by Hanson and Johansson, we can rewrite, it's not necessary, but it's easier. We can rewrite everything in this manner. And then fermion is just one object which has up and down quarks and leptons as well. And B plus L symmetry is just chiral symmetry. Then B plus L symmetry, since we have index theorem, has 0 mode. So if we take in one point insertion of its bilinear in Euclidean spacetime, that will be the expression. So that will be just a 0 mode. with some explicitly breaking U-term, like how we regularize usually the instanton measure. And here we will have proportional to mu term. They will cancel out. And after integrating over the instanton measure, we get the constant. Rotating back to Minkowski, this is real. So there is an order parameter in the standard model, which indicates in my oversimplified standard model is just bilinear. In one flavor standard model, there will be QQQL here. And this breaks, this condensate breaks B plus L spontaneous.
But your
IR is spontaneously broken.
but your result is not proportional to mu. You
No,
said
it's not proportional to mu. It's independent of mu, which means it's independent of explicit B plus L breaking. So whenever I bring mu to 0, this result stays as it should be. Like in one flavor QCD. In one flavor QCD, we instantons, we can show that there is an order parameter which breaks U1 anomalous. It's exactly similar. Right?
Right. Yeah, but no, that's true. But I thought that U1 symmetry by Ansel-Johansson is the one which is not broken and by instanton, and you are saying that it is.
No.
Right?
U1 symmetry B plus L is broken by instanton because there is word identity which tells us that conservation of B plus L is proportional to WW dual. It means B plus L symmetry is broken by 1 unit.
Okay, but then yes.
That's why B plus L can rotate away the theta parameter or theta angle, because the anomalous symmetry can rotate away. It means B plus L symmetry
has
0 modes. Once we insert the 0 modes in same point and integrate over instanton measure, we get parameter.
But in Johansson, Ansel-Johansson way, then you would say that together it would be non-observable, right? But
Theta will be non-observable, and why it is non-observable from here it's evident because it will be phase of this condensate and phase of the condensate can be absorbed in the particle. Like QCD phase is non-observable because it can be absorbed in eta prime.
Okay.
Here it's similar, like this phase can be absorbed in eta weak. Right?
But in this sense, it is still if it would be just a repetition of Ansel-Johansson, you are talking about additional symmetry as compared to the one they considered?
No, I'm not talking about additional symmetry. I'm using B plus L.
The same symmetry.
Absolutely the same symmetry. If I take B plus L symmetry, then I know there are 0 modes, right?
I see.
The simple trick is nobody computed this correlator in one point each session. That's what I observed. Right? Okay, then it means like we have goldstone. That goldstone shifts theta away in d pi r. It makes WW correlator with gap. Maybe it answers your question. Right? So it means we have composite particle. Now, what is part of the gravity? So in previous slide, I considered that B plus L symmetry was exact. That's why theta was unobservable in the standard model. Standard model, which we know it is exact. B plus L symmetry at the 3 level is exact without anomalies. But what if we have this type of high-dimensional operator in our theory? Then by B plus L, we cannot rotate theta weak away anymore. So there is the role of gravity. Gravity demands these to be unphysical. It means like we should make B plus L symmetry good. So B plus L symmetry should still rotate away theta weak theta angle, which means we should add axion-like or Pechery-Quinn-like construction in the standard model if we want to keep this type of operators. So we should make B plus L symmetry good. And making B plus L symmetry good, we still make theta weak and physical, so we still predict eta weak. This is in the resonance of the eta prime. Eta prime is mostly consists from the quark condensate, but it has little bit mixture if up quark is not zero with something external, some Peche-Quinn, right?
Without gravity,
Right.
like what would be your prediction for the binding energy of this beta weak? I mean, is it some exponentially bound thing? Because like you could have like
So,
state of a neutron
yeah,
neutrino or something.
Yeah,
And
it's
then
very good question.
It's like
It's very good
extremely
question.
huge, right?
It's a very good question, and we had a lot of discussion and fighting over that. So if we oversimplify the standard model, then that particle, like if we say that quark and like in that oversimplified version, quark and lepton are masses. For instance, let's forget about Yukawa masses. Then instantons gap them, and below their gap there will be this ghost. In the realistic standard model where we have Yukawa couplings diverted so, the zero modes are still there. That was shown by Rubakov and company. But their forms are not known. So I cannot give you effective cutoff of EFT. So where we have this eta particle, and from which point there enters elementary particles of the standard.
Just to give us an idea, you think it's electroweak size, UCD size, or
I think
inverse electron
right,
size?
right. I think decay constant will be around the electroweak scale, but cutoff of EFT will be around of neutrino physics. But may I will take these words back because we are working on that. I don't know where is cutoff of EFT. We are working on that. In QCD, everything is clear because there are no separation of scales. Everything is lambda QCD. Here, I have exponential separation of scales. I have different scales from the fermion masses, so I cannot write an EFT in a consistent way without going in like some crazy instanton computations, which we haven't managed there yet. That's why I cannot give senses on the scales. We have some intuitions, but maybe it will be wrong. Okay. The thing is, okay, around the mass of this particle, which is possible to compute by Witten-Veneziano formula, it works very well here as well. Around that, there is this particle. But how much is the playground of that particle from which we should switch description of B plus L symmetry via neutrinos, electrons, and so on, that I don't know. Unfortunately. But we are working on that project. So this statement is d pi r. This particle exists in d pi r. In d pi r, B plus L is broken. But what is effective field theory cutoff of that, I don't know, unfortunately.
But I mean, I think the issue is also you're in this Higgs phase, right? So you
Yes.
define composite, right? I mean, phase here, so you just have a state. You can't identify constituents.
For instance, in the toy model where I have massless fermions, I can.
Those were the fermions.
If Yukawa couplings of the fermions are zero, then I can. And I can immediately give the cutoff of the theory, which will be instanton generated mass of the fermion. That's it.
But the constituents here again,
yeah, absolutely, absolutely. Constituents there are the same, and the quantum wavelength of this particle is enormous, exponentially. Yeah, absolutely. Here it is a little bit different because Yukawa couplings are creating a hierarchy. They reshape the zero modes, and to work in the zero modes whenever Yukawa couplings are included, it's extremely hard. So I don't have answer. In a toy model in which I take quark and lepton massless, then I can tell you what is EFT. Quark and lepton gets gap due to instanton. Below that gap, there is eta weak. Upper that gap, they are elemental. So, like in QCD, like they are quarks, and below that there is eta prime. But in the realistic standard model, because of Yukawa coupling splittings, I don't have answer. Analytically, it's practically impossible to compute it. It's a little bit computer algebra, and we are working with it.
So just looking at the result,
Right.
this is something basically is an axiom.
Right.
So you're going to couple it to in Lagrangian to what?
So if I want to write down an effective theory which violates B plus L exactly, then it means this guy will be physical again, right? So, but here there is a role of gravity. Before that, in this discussion, I didn't mention gravity at all. Now, again, the gravity requires this to be unphysical, which means as soon as I write down this operator, I should make its phase dynamical again. Like axion in the QCD. If I want to write down a quark, then I should integrate in axion.
Just a little puzzled that if there is a scalar or massless scale or whatever,
Right.
small mass scale
Right.
that has this kind of quantum numbers QL, then you can take a baryon and decay the electron and that scalar, that's small. And then this is like not right.
No,
Very forbidden.
sure,
Because
but
your scales like here.
sure. No, what I'm saying. In the standard model, I don't need to write down this operator. In the standard model, I don't need it. But if baryon is decaying via this channel.
If you have a degree of freedom, like you try to argue,
Right.
that has internally kind of the quantum numbers similar to,
Yeah.
to that operator,
Right.
then what prevents a proton to decay to a positron and
Well, I have answer to that. Nothing prevents that. Actually, they are electroweak instantons, which mediate that decay without that scalar, but effect is small. Effect is small, that's it.
But this one, you think it will be exponentially suppressed as well?
No, what I'm saying here on this slide, what I'm arguing, if I go in the physics beyond the standard model, and I explicitly break B plus L, then the theta angle is again physical because anomalous symmetry is blocking explicitly, which means gravity will be met. So I should make rotation of this happen again. How I can do that? From the QCD, I know the mechanism. I should integrate in new degree of freedom axion, which will mix with eta weak. Like in the case of QCD, I integrate in axion, which mix with eta prime. Whenever a quark in QCD is not zero, I need axion, which mixes with eta prime and nullifies topological susceptibility. Here I'm arguing same thing. If the gravitational, if you take gravitational argument from me, then this should be unphysical. As soon as I write down proton decay operator, high dimensional operator, it should be supplemented by axion-like particle. That's the message.
But you're using the axion solution of strong CP, but we have other solutions. Would that also work here? For instance, we can spontaneously break CP. We can have solutions.
So
we can embed the
yeah.
standard model in parity invariant
Right.
theory.
Right. For
Why
me,
is it inevitable
yeah.
that you're going to have
Right.
this so-called axion?
Right. For me, in this framework, in gravitational framework, solving CP problems means making where is it? Yeah, this type of correlator 0, which means it should be exact chiral symmetry, which is coupled via anomaly to this operator. That's the state. So in the gravitational framework, there is only solution.
Is with an axiom.
Well, it's with an axion or massless upquark. Or in general, let's state both of the solutions together, that there is only one solution with exact chiral symmetry.
But I can have a parity solution, right? With respect to parity, I can have SU2 left, SU2 right. I can embed the standard model, which is parity variant solution. Can that work here as well?
No, because in the framework of gravity, this type of correlator should be there. For the QCD as well, yeah.
No, you want to make free-form massive.
Yes,
Use
absolutely.
So you need axiom.
That's why I need the exact
But
axiom.
what I'm saying is that the only way to avoid this.
Yes.
But did I got you right that you are saying that this kind of pure electroweak theory, no, I mean without QCD, and
Yes.
and you say that this Eguchi-Hanson statement that Theta-w is non-observable should be associated with the existence of new particle, or it's
Yeah,
got you
with existence of some composite particle, yes.
Okay, but what mean composite particle? In electroweak theory without QCD, I can say that it is a weak coupling. There is no composite particle at all.
But I argued that this condensate is created, right?
Right, but how it could be created if there is no any sufficient interaction there?
I think there is, because once we have instantons, they
Yeah.
have collective effect, and
Okay.
number of the W's which is required by instanton is inverse of coupling square.
Okay.
So the instanton has collective.
Okay, so you are saying that they are not decoupled even in the limit where coupling constant goes to 0?
Right. But the thing is, in that sense, okay, we are pushing, let's say, exponential suppression to infinity, then it will go 0. Because whenever coupling goes to 0, okay, this exponential factor dies,
okay,
right?
okay, but
what I'm arguing, there is collective coupling, which
so you
creates instantons, like number of the W's in order to create an instanton.
Okay, agree. But then you are saying that this exponentially suppressed interaction is sufficient to make a composite particle. I think
it's sufficient to make composite particle in deep ion. That's what
I do not think it's
possible. Very long wavelength.
No, okay. It's a ultra weak interaction with exponential, and ultra weak interaction cannot give you a composite particle. It's impossible.
But I have two arguments there. One argument is there is a condensate, and Noether's theorem is applied. The second argument is the following: that whenever B plus L symmetry kills that correlator is gapped.
Okay.
I have these two arguments, and they match with each other. The thing is,
I think it's a formal. I still then you should see how this kind of composite state could be created. I do not think.
Right. Then I'm arguing that there is collective coupling.
Yeah. Okay.
Which is strong because the coupling is alpha, right? Each of the W's couple with each other by alpha.
Yeah.
If I collect N, which is inverse of the alpha, all of them will couple with order 1 coupling, like Hartree-Fock in the atomic.
It looks like kind of making a focus, right? You are saying, there is nothing there, and then there is a dove there, and
what I'm saying is near the vacuum. It's near the vacuum for extremely long wavelengths. Extremely long wavelengths.
Then you are saying that in the theory with weak coupling there is a strong coupling, and we do not see it. I got your point, but I could not agree with it.
Because whenever we have instantons, we have strong coupling, right?
No, not true. Instanton is do exist in the weak coupling. It's not
even king. Let's discuss king. If I have king and I'm describing king as a composite, each composite lives in the Hartree-Fock approximation where it attracts the other composites. That's why we are creating king, right? Number of particles in king is equal to
no, but just a moment. King, it's not the same as composite particle. King, it is interpolation between different vacuum and boundary. It's not the same.
Absolutely. But the analog of the king here will be vacuum condensate.
Oh, right, but then when you're saying particle, it's not this. You're saying that there is this. Okay.
Whenever we have vacuum condensate,
okay.
Vacuum condensate carries a phase.
Okay, so then you are saying, I got it, but then you are saying that there are different phases, right? And there is king between phases. Then it could be the case, right? But so it's not just condensate; it's a different condensate, and you have interpolation between them, right?
Yeah, absolutely. What I'm writing here before the last line, it's a condensate, but this condensate has phase which is exactly B plus L phase. Right.
Okay.
Because
I got it.
Psi dagger psi carries B plus L unit number of B plus L. Yes.
Okay. No, thank you. I got the point. I still need to think more.
But thing is, exactly that same problem bugs us, and we had constant discussions that what is cutoff of EFT? Exactly, because we are in weak coupling, and what is cutoff of EFT? Because that EFT cannot continue to the weak scale or Schwaller scale or something like this, because that EFT should have cutoff, right?
Okay. No, I got to. Thank you, Otari.
Right. That is open question actually, and I would be more than happy and if I will get some kind of answer to that.
Okay.
Yeah.
Maybe you could just summarize now.
Oh, sure. Oh, sorry. Yeah.
Okay, great.
So my talk had two, or maybe it was a little bit confusing because it had two parts. I wanted to bring two different papers. So here what I argued, that quantum gravity works only on Minkowski with cosmology. Then in quantum gravity, we have instantons, which make topological structure of GR, namely Theta-vacuas. And this defines CP problem, which we call gravity CP problem, and it has only solution in the framework of supergravity. As soon as we are solving that problem, we are breaking supergravity as well, and then we are predicting that there is axion-like particle in the case of supergravity, and there is gravitino, and their masses are related. They are almost degenerate. Also, we restrict representations on one-half Fermions. I didn't explain this in details to spare some time. And yeah, it gives actually very strong constraint on neutrino physics. For instance, right-handed neutrino should be in spectrum and so on. The second part was a weak part, that I argued that if we have exact B plus L symmetry in the standard model, since it removes vacuum angle dependence, at d pi r it should be supplemented by some kind of Goldstone force, which is eta w. Then I argued that there is B plus L violating condensate, which is formed and the quantum numbers match, so there should be this part. I didn't give answers which we struggle, so on what scale it is created and so on. It's a hard questions. What we know in d pi r, there is this particle. And then I argued that in the same gravitational framework, B plus L should be good symmetry, exclusively broken by anomaly. Okay, I think that's the outline of my talk.
Any other urgent questions for Otari? I think we had a lot of questions in the talk, but any other questions? Well, if not, of course, Otari is still here for the rest of the day, right?
Right.
And so he can definitely drop by and see. So let's thank him again. Thanks, Otari.
Thank you very much.
Thank you. Okay. I'm sorry, Otari, that maybe I asked too many questions, but
No,
thanks.
I'm more than happy to have questions because I worked on this project a couple of years. So
Okay. Thanks.
thank you very much for your questions.
Decide